Yes, sir.
Okay.
Yes, sir.
Hello, sir.
Yeah. Hello. Tell me.
Sir, in previous week, in calibration plot, I have a question, sir. It's a problem, sir. Once more time, you can discuss.
Definitely, definitely. Okay. Today I will discuss. Then I will start from the calibration curve. So can you
Okay.
please briefly tell me that which step is not clear to you? Please tell me first.
Why, sir? Use of deviation, standard deviation. Use of standard deviation.
Means how we can get the calibration curve, then we can predict the how we can plot the I mean, 3 times standard deviation, then limit of detection calculation, unknown sample predictions, right? All the things.
Yes, sir.
Okay,
Yes,
okay,
you can say once. Yes.
okay. This is very crucial part for the biosensor. Okay, I will repeat one more time for all of you. So. So still 24 students. So I will request to please join on time. So you should be here.
Sir.
Yeah, Bhavesh, tell
Hello.
me. Yeah,
Sir,
Bhavesh,
I
tell me.
also have some issue with the detection limit, sir. I'm not confident. I think, sir, if you can repeat it once, means briefly, then it will be helpful.
Okay, so means what is the limit of detections? How we can get it, right?
Yes, sir. Like means after every step, I used to get confused, like what was happened before. So that's why.
Okay, okay, sure, sure. Okay, let's repeat the limit of detection that part also. We'll.
Sir,
Hmm.
sir Vibhuti here, sir. You can take an example of the standard deviation, sir. Last time
Yeah,
you said,
yeah, I already mentioned here standard deviation like one example I can take. I will show you again. I will repeat.
okay, okay, sir.
Hmm. Okay, any more questions? See, I'm going to tell you because I already mentioned last week that we will have a exam. Total 3 exam we have to take for this semester, means for written exam, and then one or two more presentation. So first your written exam will be on Wednesday, 10th of February. February 10th. So this Wednesday, February 3, then next Wednesday. So this Wednesday, I will discuss again some questions answer from your side. You can ask some questions. I will give you some questions. Then we will discuss on Wednesday. So up to today, I will cover some more topic. Then we will discuss again all the different kind of questions from the first class to until today's class. Then you can also ask me some more questions on Wednesday. Then I think we'll get one more class on Monday again, right? Yeah, that's possible. We can take one exam on Monday also if you want. Yeah, I think it's better take the exam on Monday then. Okay, so let's take the exam on next Monday. Today is now 1, so 8. So 8 will be our written exam date. Okay, so next Monday we will have our written exam.
So what is the pattern of the written exam?
So pattern will be all kinds of like some descriptive, some short type, some MCQ. Also, I will give you some like I will give you some calibration. You have to determine the limit of detection. You have to draw some maybe some biosensor. This kind of things I will give you. Okay. Basically, so you have to write your all the answer on your answer sheet on plain paper by pen, something like this, and you will take the screenshot and you have to make the PDF and upload. So I will give you 1 hour time for your question answer. Then after that, I will give you maybe 15 to 20 more minutes for your maybe you have to take the screenshot, then make the PDF for uploading on MS Office. This Microsoft Office in the assignment section, I will give you the question. So there you can upload your answer sheet. Clear? So that
So
Okay.
how many questions?
so this time I will give you total 20 marks.
It's a number of questions actually, not marks.
Or number of questions 20 marks. So maybe around 10 questions.
Like one line answer or paragraph answer?
That I mentioned just now. Means some questions will be with some descriptive type, some will be the MCQ type, some will be maybe like I will give you some diagram, something like this. You have to calculate something lipid of detections and what kind of biosensor is this, or maybe I will ask you to draw some biosensor design, something like this. Okay, maybe I
So
will
like
ask you
a
to.
mid-sim.
Now this is not actually mid-sem. This is just before the mid-sem kind of this. So but this mark will be added to your final evaluations time.
Okay.
Hmm. So 20, then next time again I will take again 20. Again the third exam I will take again 20. So total 60 marks I will take. Okay, so let's start the limit of detection. These things, just a minute, I will start. Okay. See. So first, let's start from this slide. See, you can see here that at first we are designing here a biosensor. So let's, so like this, as I mentioned in the exam also I will ask you design a biosensor. So in this case, how we'll design, so you have to first you have to choose a transducer, I mean the material of the electrode. It can be some I2 electrode, it can be gold and carbon, but this exam you can choose like a transducer, no need to mention the electrode name. So that electrode, maybe after this exam I will teach you how you will choose which one is the better, that I will let you know. So first you can choose a electrode surface, then you can immobilize a surface with some linker molecule we need like avidin. So as I mentioned that avidin and biotin, they have strong interaction. So antibody that already conjugated. So this one is a biotinylated antibody, right? Biotinylated antibody. So that's why if we drop it for like 15 to like 30 minutes, maybe we can give some longer time for better immobilization. Then you can wash it. So which one not bind on the surface, they will be washed out from the surface. Okay, they will go away. So you will get just on the surface, just antibody coated surface like this. Not only one, there will be so many antibody on the surface. Okay. So,
Hello, sir.
hello.
Sir, why you use Aberdeen?
Why I am using avidin? So here
Yes.
actually, why this is avidin actually helping to bind the biotin that conjugated with the antibody. Because as I mentioned that avidin and biotin, I think you missed the class. Avidin and biotin, the conjugation time, right?
Yes.
So you should follow the class, otherwise you will not get good mark in the exam. So as I
Okay, okay.
mentioned, because I am always taking your attendance and I am checking so who is present, who is not. So depending on presentation, I will give you 20 marks in the final exam. This is very, very important. So maybe, so if your attendance is very good, you will get full 20 marks. So be careful. Okay. And and basically, see, I will, if you don't understand these things, just ask me. I will repeat. And don't think about this is silly question, something like that. I'm repeating again the same thing. So I will repeat the question. But
Okay.
you should be in the classroom.
Oh,
Okay, so why I am using the avidin? Because avidin and biotin, they have the strong interactions. Let's go back. So if we add the biotinylated some molecule, they can easily bind on the surface. That's why. Clear? So this antibody are actually conjugated with the biotin. This color one. This is the biotin. So that's why they will bind on the surface. So like this way, we can get a biosensor surface that coated with primary antibody. Now clear?
okay, okay.
Okay. Now what we will do? Now we will add the sample, right? So this is the sample. So this is the total biosensor formation. So if I ask the questions in the during the exam, so this whole the steps you have to describe. This is the biosensor, total biosensor design. Then we are using the sample. So the sample content your target, right? So this target If your sample contain target, then only it will bind. If there is no target, then it will not bind. Then secondary antibody that conjugate with the gold nanoparticle, that also not will bind. We should have target on the surface. So if it is target there, then it will bind on the one epitope of the antibody, that is called the epitope antibody. So then target will bind on the surface. Now see, so after binding the target, so we have to wash. So we have to, how many times we have to wash? See, first avidin, then on the avidin coated surface we have to bind the primary antibody that biotinolated, then we have to wash. So number one time washing. Then second time we have to add the target, then we have to wash. So why we need to wash this target step? Because if there is the other non that is not bound on the surface, if the target is just here and there on the surface, they should removed from the surface. That can be done by washing step. Maybe there is some more antibody. There is some maybe. So that is just for example, I was showing one antibody, but there is so many antibody, thousands and thousands of antibody here. So maybe some target will be bind here also, and some target may be here also. So it should be washed out from the surface. So you know why we need washing? If this target is there, and if you not wash properly, what will happen? You know, so when you will add the secondary antibody, this secondary antibody that contains gold nanoparticle, then it will bind here actually. Not so this is not specific position, right? So this target actually somehow it is adsorbed, not because of the antigen antibody binding, somehow adsorbed, right? So then some secondary antibody can be here because of this antigen. So and this antibody that is gold nanoparticle conjugated. So this is some non-specific binding can possible, right? This is non-specific binding. This is non-specific binding, and this one that is target and gold nano conjugated. This is the specific binding. This is specific binding. Make it clear. This is very, very important. Which is non-specific and which is specific. So specific one, which is on the antibody coated, antibody and target, that is actually we need. That is our requirement. That is we are waiting for, right? This binding.
So that is
Not
the
this.
primary antibody.
Yeah, primary antibody coated, but not this one. Also, another possibility there, not only target, maybe sometimes the target is not maybe absorbed. Just think about the zero concentration. Just think about zero. Like this is the transducer, and here the antibody coated, right? So if your target, if your sample, suppose your sample does not contain any kind of target, so no target, but you don't know, right? Sample to contain target or not, but you have to add the secondary antibody that conjugated with gold. Then only your sensor formation will be complete. So you are adding the next final step, secondary antibody to conjugated gold nanoparticle. But if this gold nanoparticle conjugated antibody binds somehow on the surface of the transducer, then this is also non-specific binding, right? So specific binding, if it is bind on this primary antibody coated surface, this is the specific one. But non-specific one, if anywhere in surface, or maybe somehow if somehow maybe electrode is exposed, that can be attached on the exposed area, or in the evidence surface, anywhere, if it is bind the secondary antibody that is labeled conjugated like gold. So gold is called here labeled and this is the labeled antibody. Gold labeled antibody. So this is called non-specific binding. Clear? What is the definition of non-specific binding? So if the secondary antibody that conjugated with label, if it is bind instead of on the primary antibody coated, I mean the antibody, then it will be the non-specific one. So this is the specific surface. Anyway, so actually this non-specific binding can cause your higher background. It can cause higher background, right? So why it can cause higher background? Because see, what is the background current, right? Now the questions will come, what is the background current? That I already mentioned last time, last class, that I am repeating again. So background current means like the zero concentration current, right? So if your target not contain a zero concentration, no target, then I mean, here you are although adding your sample and you are washing, but there is no target. That's why nothing will be here on the primary antibody. Then your last step, you are adding a antibody that is gold conjugated. So when you are adding this one, so on the surface it will be here and there, but you need washing. Then only this will be go out from the surface. So you are washing, then it will go out. But somehow, if it is here, so then although we are thinking this is background, right? There is no target, so we are thinking it is background. But as the secondary antibody already bind non-specifically on your surface, then this gold catalytically will react with your substrate and it will form the product. And this product will be oxidized on your surface and will get the electron transfer. Basically, then background will be increased. Make it clear. Why? Because of non-specific binding, background can be increased. So basically, your sensitivity of your sensor will be decreased during that time. Your sensitivity, right? Sensitivity. When we will get very good sensitive biosensor, when we will get higher signal to background ratio. So when what is background? The zero concentration. That is background. So if background low, then only we will get the signal to background very high. But if somehow your secondary antibody that is conjugated with gold somehow non-specifically adjoined on the surface, because of catalytic reaction of the gold and substrate, it will form the product, and this product will be oxidized when we will apply some potential, like 0.5 volt we are applying. During that time, this product will be oxidized and release the electron. So that basically you are getting background. Clear, guys? Or I should repeat? So please clear this one. This is very, very fundamental things of the biosensor. Just
So
learn it first.
that sensitivity part, please, sir, can you just repeat once? Sensitivity part.
Sensitivity, right? Okay. Okay, let's discard it. So what is sensitivity? So because I am writing on the touchpad, so that's why my handwriting sometimes is different. Don't mind. I am writing on touchpad. See, sensitivity is kind of signal to background ratio. If you are getting very high signal to background ratio, then your biosensor will be ultra sensitive. Ultra sensitive means you can reach around femtogram per ml concentration target you can reach. But so how you can reach there? So there is two possibility. How you can make your biosensor more sensitive? Please, can you tell me? So what is your name? Who just you asked me question? I cannot see actually.
Sir Bhupendra.
Oh, Bhupendra. Okay. So can you please tell me what is the how you can increase the signal to background ratio? There is two possibility. Tell me what is the two possibility here?
By first increasing the release of the current, basically signal is what we are getting when there is no sample, and
Right.
if we are, yes sir.
So if you can increase the signal, then your S by B ratio will be very high, right? If your S is very high, then definitely you will get S by B. That is, the ratio will be very high, right? Right?
Yes sir, yes sir.
So that is high.
Yes,
It means this is highly sensitive. Or another way, somehow you already reached the maximum signal. I mean, a very high current you got. You cannot increase the current more than this. The signal current. Signal current means after dropping your target, then you are adding the secondary antibody that conjugate gold. That is your signal current. So that is already saturated. That much only you can achieve. So what you can do? You can decrease the background, right? If you decrease the background, then S by B ratio will be very high. That also second process. So that's why I'm telling here.
Sir, how can we decrease or increase the background? I mean,
How
we can decrease the signal, but the background noise will also increase.
Repeat again. Who are you? Your name? Aksant, right? Good questions, Aksant. Agrawal.
Yeah,
So,
if we increase the signal, the background will also increase.
So that's why that is the main challenge we are facing. Then only we can develop a ultra sensitive biosensor. So that is called the ultra sensitive. So how we can do this? That also I will teach you. So there is two possibility. One, increase this and decrease this. So how we can decrease? So that we can do it to minimizing the non-specific binding. So somehow you achieve very good signal, right? This is gold nanoparticle. So it will react with substrate and form the product, and that product will be oxidized and it will release the electron. So this is the signal, right? This process is the signal. So this is, you are getting very, very good, very high. But somehow your some antibody actually can bind on your surface, and it is because it is actually can increase the background, right? So you should remove this one. So how you can remove it? So there is one process, is the washing with, you have to washing properly, very good way you have to wash it with some BSA, bovine serum albumin. So this is one kind of the protein. So if before adding, I mean, just I will tell you. So how will it decrease the non-specific bind this one? So this is your primary antibody coated surface, right? During that time when you are washing, that time you can add some BSA. So that BSA will adsorb on your surface. This is very small molecule, very small. This is almost I think 1,000 times or more than this, smaller than the target. This is very small. So they will cover, that is the unoccupied surface. They will cover. So what happened? The secondary antibody, that is golden, they will not get any space to bind on the surface. Like this way, you can minimize to bind this secondary antibody on the surface. So basically, you are decreasing the background. So this is one way to decrease the background current. So you can, if you can decrease this one, so basically you will get very high signal to background ratio. Okay, Agarwal, is it clear now?
Yes, sir. Yes, sir. It's clear.
Sir,
So basically the main thing, you have to use a washing buffer, washing solution, washing solution. So this solution will contain some BSA. So what is BSA? This is bovine serum albumin. This is a small protein. So when you will add this one, so after coating the primary antibody while you are washing, so you can use this kind of the washing buffer or washing solution. So while you are washing, this small all the BSA, they will occupied this unoccupied, some unoccupied position on the electrode. They will bind. So basically the secondary antibody, they will not get any position to bind on the electrode surface. That's like this way, you can minimize the non-specific binding. But although it is 100%, you cannot do this. I mean, most of the non-specific binding you can avoid, right? Because there is still, they can get some narrow, some nano size position, they can bind. But you can avoid non-specific binding, not 100%, but almost maybe 95%, something like this. Okay, Vibhuti, you are asking something, right? Yeah.
sir, hello.
Yeah.
Sir,
Tell me.
sir, all these things are just after dropping the sample, these things are taking place simultaneously. So, removing the unknown, I mean to say that all these reactions are taking place simultaneously. We don't have any our will to just stop the reaction in the midway between so that we can increase or decrease the background. So, how is this possible, sir? By just washing with this, we can minimize the non-specific binding.
Yeah, so what you will do, so just take the electrode, then you can add the avidin, you can take the avidin. So so there is so many way, you can think some creative way. So this is, you can freely you can think. So just what you can do, you can add the avidin, then you can drop some BSA solution. So they can go to the some this pore size, right? That is not covered by avidin. Clear? They can go. Then you can coat the primary antibody, so they can come. But again, after adding primary antibody, again you can add some BSA. Then if there is some any unoccupied position, they will go and they can adsorb this unoccupied position on the surface. Like this, then you can, now you can add the target, and even in the target solution also you can add some BSA or 2020. So there is so many surfactant can also help to avoid this kind of non-specific binding. Clear, Vibhuti?
Yes, sir.
Sir. Yes, sir.
Okay. Okay, so this is the this is thing. So let's come to now detection limit, this area, right? So see, this all the steps I am every day. I sometimes I will repeat so that some common question will come and we can discuss. Okay, so this thing done, right? Okay, I think let's skip it all the diagram now. Okay, yeah. Okay, so our biosensor already formed on the surface, right? Now what we'll do, we have to add some chemical that I'm always asking. This is the total biosensor. So after this sandwich formation, we have to add some chemical that is called substrate. So this substrate will react with this nanoparticle, will form some product. So this product, I mean, I bring it here. This product now on the surface will react. How it will react? We'll apply some potential. Suppose 0.3 volt, some potential will apply. Potential will apply. Volt. Then electron will be released. So that electron will be, we can measure by the help of cyclic voltammetry, or like this way. If we increase the target concentration, more and more nanoparticle will be on the surface, reaction rate will be higher, and you will get the higher current. So slowly, like 0, 100 femto, 1 pico, see the current increasing. Or we can do the chronoamperometry. So if you increase the target concentration, the current will be increased slowly with respect to concentration. Or in the chronocoulometry. So if we change the concentration from 0 to different concentration, so you can see the charge will be increased. So why charge will be increased, that I already taught you, right? Is it clear until here?
Yes, sir.
Yes, sir.
Okay, now come to the calibration curve. So for getting the detection limit, so after you have to make a full concentration chart. So this chart you should have in your hand before getting the calibration curve. Not only 1 pico, you have to get at least 7, 8, or 9, 10 concentration you have to get, not 2, 3. Then only you will get the full calibration. So then what you will do, in each concentration, you have to check at least 3 data. So at least 3 data you have to measure. Suppose in the 0 concentration, you are getting how much current, how much charge you are getting here. Sorry. So I cannot draw properly. Because, so 0 case, suppose you are getting this much. Okay. Suppose you are getting this much 0. So it is around, suppose 0 0.27. So 0.27 millicoulomb. This is your 0 charge. So you have to measure 3 data on the similar biosensor. Like you have to prepare 3 sensor. They are similar, not the same. 1, 2, 3. So they all are primary antibody coated. Okay, so you drop the sample and your sample does not contain target. That's the secondary will not bind. When you are washing, all the gold nanoparticle coated conjugated antibody will be washed out. So this is your final step for the 0 case, right? 1, 2, and 3. So from the 1, maybe you are getting this much millicoulomb. From 2, maybe you are getting 0.28 millicoulomb. And from 3, maybe you are getting 0.275 millicoulomb. It's possible, something like this. They are very close, but not same. Right. Now, you have to get the standard deviation. I mean, what is the mean value? So if you, I mean, if you use the Excel, then you will get this kind of structure. So this will be your mean value, and you will get this the deviation from this to this. So actually, you are not getting for this is for 0. This is for 0. It looks like this. Means your current, sorry, your charge actually deviating from here to here. I mean, from 0.27 to 0.28. 0.27 to 0.28 is divided. So this center is your mean value. Clear? Clear, guys?
Yes, sir.
So this is for 0. Same thing you have to done for all the concentration. So now you can take one concentration like 10 femto, right? So again you have to prepare three sensor for 10 femto. So primary antibody coated, primary antibody coated, primary antibody coated. So your target concentration is very, very low, right? So maybe only one target will bind. Although you have thousands maybe antibody on the surface, maybe one antibody will bind with your target. Huh? Because of one antigen, you will get one secondary antibody that is conjugated with gold. Huh? So similar way, maybe they will bind for because this 1, 2, and 3 they are the similar. So maybe here also you will get one, but maybe somehow here you got two, maybe because of some error. To minimize the error, I mean user error, that's why we are using the 3 sensor, not the only one. So only one is not. We are not considering this is sufficient for a calibration. At least you have to measure 3. So maybe for again for 10 femto case from 1 maybe you are getting 10 femto maybe you are getting around 0.3 like 0.35. So here maybe you are getting 0.35 millicoulomb. Maybe second case also maybe you are getting 0.36 millicoulomb, but because here because of some error you are getting maybe around 0.4 millicoulomb. So then you have to within these 3 data you have to again collect the standard deviation and mean value, right? So like this way, okay, so let's come here. Yeah, suppose this is for troponin I detection. So this is the full concentration chart here. Okay, this is the full concentration chart here. So from here, like see, like all the concentration case we plot it, like 10 femto, 100 femto, 1 pico, 10 pico, like this all the concentration we got. There's so many concentration, like 10 times, 10 times, 10 times we increase the concentration. This is the standard deviation and mean value. Clear? Here we only shown 1, 2, 3 concentration, but here we shown 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 concentration we have taken, and their mean value and standard deviation value. Okay, and here applied potential maybe we applied actually 0.05 volt.
Okay, sir. Yes.
Yeah. Okay. Now, how we'll calculate the limit of detection? So, as I mentioned, for limit of detection case, we will consider the zero concentration data because this is the minimum. I mean, what is the definition? Now, come to the definition of the limit of detection. The definition is by using your biosensor means lowest concentration you can detect. The lowest concentration you can detect, that is your limit of detection. Now that how you can calculate the lowest concentration? See, so for that we have to think about the zero charge we will measure first, right? In the millicoulomb, zero charge you have to measure. Then how much above than zero? That is your limit of detection. So for that, first we will take the 3 sensor, number 1, number 2, number 3 sensor, and we will measure their like standard deviation and their mean value, right? So we will measure like here standard deviation we measure suppose x. So for the 0 case standard deviation is x. Now to minimize the user error, as I said last time, we will multiply with the 3 with the 0 standard deviation. So that what will happen? Although like this is your 0, sorry, see here we are drawing like this is your 0 current line, and this is your all the concentration. This is your all the concentration, the standard deviation error bar here, right? So this is your 0 line. Now as you are multiplying with 3, the 3 times standard deviation line will be increased than this, right? This is 3 SD. This is the just 1 SD, and this is 3 SD. So why we are doing this? Because actually it should be the limit of detection, but to minimize the user error, because maybe sometime I am maybe using the sensor, I am getting some current. When maybe Vibhuti you are using, maybe he will get some little bit lower current. But when Samir using, maybe he is getting a little bit higher current, right? That's possible, current or charge. That's possible, man to man. But the same, similar sensor. So that's why we are thinking let's increase by 3 times so that we can minimize the user error. So it will we are using actually this bar as the zero line. Actually, this is the zero line. This is the 3 times standard deviation line in the calibration curve. This is actually now become zero line. So now, if you draw a line, straight line with this all the concentration, which one intersect with your this line, 3 times standard deviation line, this will be your limit of detection. I mean, this much lowest concentration actually you can measure this intersect line. So you can draw a line. So sometime last class you asked me question. Maybe they are not straight line. Maybe something like this, right? Something like this. So what you will do? So you can do something like you can use first few points. If they are behaving as a straight line, you can draw a straight line. Otherwise, you can do another thing. You can do like this way. You can measure and you can go. If like this way also you can draw a, or you can extrapolate the line. So it will match with certain point with your 3 times standard deviation line. So this will be your actually lowest concentration you can detect with your biosensor. Clear, guys?
Hello, sir.
Tell me.
Sir, I have a question. Sir, if the line intersect the three standard deviation line in negative concentration line,
I mean
then what?
here.
Yes, here.
No, then that is not possible really, right? This is not ideal, right? This is not ideal. So what happened? So sometime, so what you will do? Okay, I'm drawing. This is a very good question. So how will let's discuss all the things. Suppose, so you are extrapolating, but they are going to the negative side. So actually that's not possible. So basically what you will do, so that only possible in this case. Like if it is not straight line, sometime like this it's possible. Like this, so it can go to the negative side. So one thing you can do, maybe few points, they are straight line. So you can draw a line here, or you can measure the standard deviation of the zero data, maybe 7 data or something like this, not the 3 data. So to minimize somehow you should get the lowest positive value you can get, not the negative value. Okay, so what is your name, please? You tell me. I cannot see you.
Suman, sir. Suman.
Shuman, right? Yeah,
Yes.
the negative concentration is not exist, right? So
Yes, sir.
somehow you should get the first positive value, that one.
Oh,
So somehow
okay.
you can measure more zero data, and you have to think about where is actually intersect happen.
Sir,
Maybe, yeah.
Sir, this
Maybe
thing would be specified in the problem, or just we have to do on our own, that I have to take 7 data or 3 data or 4 data or random any number of datas.
see, that calibration actually basically is depend to sensor. Sensor to sensor. Like if you are developing a troponin eye sensor, then you have to develop your own calibration curve. It's fully specific. This is your own calibration curve you have to measure. So basically, you can take, if you can increase the sample volume, that is actually very good. Not 3 data, you can increase the 7 data also. So what is that? What will happen if you can increase the sample volume? You can basically minimize the user error. Okay, Vibhuti. So if you measure the, you can increase the sample volume. Basically, you are decreasing the error, right? So what happened when you are developing a calibration curve? So basically, suppose here you are getting the standard deviation, and you have to mention that how many sample you taken in this calibration curve, like 3 data or 7 data. And basically, as you are actually taking the higher standard deviation, like so many sample you've taken, so basically your limit of detection error will be minimized. Okay, so if from your sensor, if your limit of detection suppose 10 femtogram per ml, but maybe you are getting suppose you are getting your intersect in the negative side, but you are just avoiding, because negative you cannot say it is the negative concentration. So you can go the more some above concentration. So you can say maybe lowest real concentration is the, suppose this one. So this is the 10 femto. So you can mention this is my detection limit, not the not the non-real. That is not real. That should not be mentioned. That you should mention that is the just above concentration that you can measure by using your biosensor.
Sir, in this aspect, I have something to more to say.
Okay, tell me.
Sir, suppose we have two detectors. One is
Hmm.
myself prepared, and I bought some other one from some other thing. So suppose from market. So
Hmm.
if we take the data, random data from these two sources,
Hmm.
so according to you, how much would be the deviation if we take into account this plot and all those things?
Say when you are getting the sensor from the market, so the people they should as I said, they should have their calibration, and that calibration should be input. Maybe they will use some, maybe some app or something like this, some maybe some algorithm they should use. So that calibration, I mean how many and how much the standard deviation of the zero, and how much lowest concentration we can take. So that should be, everything should be input inside this. Maybe if they use some app or sometime algorithm if they use, so they should be inside this device. Then only they can automatically, they can I mean convert your current to the some concentration. They will convert automatically, I mean charge or current to the concentration. Something like this. So it is not like other people doing. So some people, I mean, if you are developing a biosensor, so you have to do by yourself, and you have to tell this all the information to the industry people who are whoever going to I mean going to sell this one to market. So like this, then only based on that data they will design. I mean they will use some algorithm, they will have some app, and then they will collect this current and they will convert to this concentration, something like this. So it is kind of the, I mean based on you only, and you can do everything. But if you give this one to other one, maybe he can also design something based on him or her calibration. Hmm. Okay, so it is fully depend
Excuse
on
me,
the
sir.
calibration.
Sir?
Yeah,
Hello?
yeah. Tell me. Hello.
Uh, Sir, I have one small doubt. For example,
Hmm. Hmm.
if you extrapolate this curve, which
Hmm.
were second curve, this concentration versus what is it? Sir, can you see? Can I, that
Hmm.
concentration versus charge curve?
Okay.
If you extrapolate it
Hmm.
to that point such that there is zero concentration, but there is some charge, can we say that charge is a noise, sir?
Let's. Now, please repeat now. Which one?
Yeah,
This one.
yeah. There is a concentration one,
Yeah, yeah,
concentration of troponin one, and
yeah. You are right. This is the noise. This is the
okay,
noise.
sir.
Yeah,
Okay,
this is the
sir.
noise.
So that means from calibration curve itself, we can say that what noise is there.
Yeah, you can say this is the background. You should not. You should have your current more than this. I mean, your signal should be more than this, more than background, not less than this. So you can say this is noise or
Okay, sir.
background.
Sir.
Definitely.
Okay, sir. Sir, one more. Like, correct me if I'm wrong, sir. If the concentration just above this noise is, can we say that is the detection limit? Just above the
Just
noise.
above this, yeah. So by your biosensor, like you drop some sample concentration, you got just above this one. Yeah, that is your
Okay.
the limit of detection.
Okay, sir. Now, thank you, sir.
Yeah. So I just told you the story of the everything. Now, according to your sentence, you can write down. Hmm. You can write it by your way. Clear?
Okay, sir. Yeah.
Okay.
Sir, for a very non-linear fit, is
Hmm.
it a good idea to break my entire data to various linear regions?
Yeah, so there is so many algorithms. Some people are using some mathematics here also. Some like hyperbolic or something like. If they are not, so you have to somehow you have to fit this one. So if you use some software, some fitting software, I think Soma, you know maybe which background you're is chemical engineering. You're right.
Yes, sir. Yes, sir.
Yeah. So if you use some software, there is so many option there, like for fitting a curve. I think you know this one. You use maybe 10 plus 2 level in the
Yes,
mathematics.
sir. Yes, sir.
Yeah.
Yes, sir.
Like
Yes, sir.
hyperbolic or maybe straight line or
Yes,
linear.
sir.
There's so many things. So somehow you have to fit it, means super fit. That is the maximum you can fit this one. And from there you will get the, I mean, the maybe fitting coefficient also you will get. And that's the thing, the limit of detection you can measure just above this 3-star standardization, the concentration that you can say. Okay, Shomo.
Okay, sir. Means I meant to say that if my fitting is very much non-linear, means I am not being able to fit it nicely. My deviation, my error are very high. So in order to overcome that problem, we can we break these entire region into small sub-regions where
Definitely.
in each of these sub-region it behaves say linearly or more nicely than the overall gross picture.
Yeah, so there is two answer I will say you. First answer, if that is not like this straight line or if you cannot fit fully, so then your calibration is not a good calibration. First answer, because there is always, if you increase the constant, there should be a linear correlation or some of the correlation should be there. The first answer. The second answer, if still you are not getting this kind of correlation, then my answer will be yes. So you can fit some break, you can make a break, something like first few point, maybe first, third, 7 point you can take, and somehow you have to make the correlation. Okay.
Okay, sir. Yes. Yes.
Okay. Yeah, that's my answer. Okay. So that is the limit of detection things I repeated. So everything clear, guys? So this is the very important discussion actually. You should understand, you should make it clear. This is the very basic thing. Then only you can understand the whole biosensor design. Okay, can I go ahead or can I start new topic again?
Yes, sir.
Okay, good. So let's start new one, is the electrochemical impedance spectroscopy. Okay, so we done the fundamental things and we can measure, and we can measure also unknown concentration, everything I mentioned. So we can use, so I just use like CB is a very preliminary and fast technique we are using generally for biosensor, chronoambrometry and chronocoulometry. So this is the main three we first generally we are trying. Then we are trying impedance, EIS. Electrochemical, E means electrochemical impedance spectroscopy. So this is kind of, we are measuring the resistance. So you know, impedance is kind of the, we are measuring impedance. This is the kind of the ratio of the alternating voltage. So like V equals to IR, you know, the resistance. So this is for the DC current, right? Right, guys? You know this one? For the DC, this is the relation.
Yes, sir.
Yes, sir.
Yes, sir.
But generally, so in the alternating current case, so this is the relation. Impedance is the ratio of the alternating voltage and the alternating current. So we will measure, so we will apply the alternating current, means when we apply the voltage, everything, that is the alternating AC we will apply, and we'll get the actually impedance actually corresponds to similar to resistance. So if your surface is highly conductive, means your resistance will be very low, right? If your resistance is low, then we will get the impedance also very low. Basically the same thing. Not I can say same, this is a similar thing. So you will get the impedance also very low. So if your surface is not that much conductive, maybe your surface if bind with some very too much organic stuff like protein, so many things. If you increase the concentration of the target, there is so many protein. Basically protein is the non-conductive. They are non-conductive, right? So because that's why the impedance also, that's why will be increased. Resistance is increased, impedance also increase. Okay, so impedance, so it is proportional to your biological stuff. I mean, I can say the protein. So because they are non-conductive, and impedance will be increased. So based on this, if you can measure this impedance value, so if you increase the target concentration, your impedance also will be increased, right guys? Is it clear?
Yes.
So if you add
Yes,
more
sir.
and more target on the surface, so because more of protein on the surface, so conductivity decrease, so impedance also increase. So we can make a calibration similar way. Same like 3 times standard deviation 0 data. So if you measure the impedance value in the y-axis and x-axis is the concentration. So if you increase the concentration, maybe impedance will be here, then increase, concentration increase, impedance increase, concentration impedance increase, like this way. You will get a calibration. So electrochemical impedance actually, it will show something like this. Okay, now let's come to the parameter. Which parameter will measure from the EIS? So this is kind of, so if we, let's remove all the writing here. See, so this is your surface. Oh, it's breaking. This is surface, right? So here is something. So you are adding. You had some solution. Which solution you have? In the impedance, you have to use in the impedance spectroscopy. Generally, we are using a redox couple. Means your solution should have some electron flow should be there, right? From solution to the surface, electron flow should be there. Then only you can measure how much this is conductive or not. So in the impedance spectroscopy, in a solution, we are using a K3 FeCN whole 6 plus K4. Oh, I cannot write here. And plus we are using K4 FeCN whole 6. So here in K3 FeCN whole 6, what is the oxidation state of iron? Please tell me, anyone? What is the oxidation state of iron?
+3.
3.
Sir, +3.
Plus 3. And in the K4 FeCN whole 6, what is the oxidation state in the iron?
+2.
+2, sir.
Sir, +2.
Plus 2, yeah. So yeah, something like this way. So we'll use some redox couple, like redox. Why I say redox? Because Fe3 and Fe2, they can be converted easily. So that electron transfer we will measure through the impedance spectroscopy. So see, when we apply some, I mean, in some frequency range, when we apply some frequency or some potential or something like this. So maybe, so this reaction simultaneously will happen in the solution. Okay, this Fe3 Fe2 conversion will happen in the solution. Now, so this electron will flow through this solution to the surface, because this electron should pass through this transducer, then we will get this electron to the detector, right? So if this electron can pass easily the detector, then you will get less impedance, right? Less impedance value. And if this electron cannot cross this barrier, protein barrier, right? Here some antibody coated, right? And if they increase the target concentration, so they basically fully block the surface, right? If they block the surface, then the electron from the solution to the surface, they cannot go, right? They can't. So basically the electron flow will be hindered by this protein layer. So that's why you will get high impedance. Clear? So that impedance we are measuring by using a redox coupled solution like K3 FeCN whole 6 and K4 FeCN. This is two salt mixture we are using. Some concentration you can use like 5 millimolar or 1 millimolar, some concentration you can use. Okay, now come to the circuit design one. So let's think when actually we are adding some electrolyte solutions, it behaves like a double layer. Why I am saying the double layer, that I am going to describe now. It is kind of the. Do you have any more any questions, guys?
Sir,
Tell
so
me.
one question. So the electrons will go from the working electrode through the electrolyte solution, then meet at the counter electrode, then we'll get the current, no, sir?
No. Electron will flow from solution to electrode, and that electron now will go to the. I mean, when the many electron will pass, I mean, you will get the more current, and that will go to your detector. They can measure how much and how many electron actually flowing from solution to electrode, not electrode to solution. So this is basically you are conducting a reaction, this reversible reaction, Fe3 Fe2 reversible reaction you are conducting. So it releases one electron, right? When Fe3 convert to Fe2 or Fe2 convert to this Fe3, then it will means this electron will be in the solution basically. So
Sir,
this electron will be captured by the transducer. Okay, tell me which one is not clear.
hello, sir.
Yes.
Sir, how the protein layer will be formed, sir?
How the protein layer will form? The same thing that I taught you until I think today class. See, so you have to draw, means this is your sensor, right? Primary antibody coated. You know this one, okay?
Yes, sir.
So how will form the protein layer? So you have to add your sample. So your sample, if contain the target, then it will bind, right? So if your solution, you are adding three sample you are adding. So one sample, maybe you have the low concentration of target, so it will bind only with one antibody. Second sample, you have some higher concentration, maybe it can bind with two antibody, right? This is the second sample. Third sample with the highest concentration of target you have. So maybe it can bind maybe all the three antibody. So if you increase the concentration of the target of your sample, then basically you are increasing the protein layer on the surface. Clear?
Yes, sir.
Yes, sir.
Yeah. So like this way, your surface will be more. Surface will contain more and more protein, and basically more and more protein means basically you are hindering the electron transfer from solution to electrode. I'll show you some example. Let's show you some example here. See, so here, see, this is the so here the 3 oxidation state, here the 2 oxidation state. This is the electron transfer happened, right? 3 to 2 electron transfer happened. So basically, so these things means this electron should go here. Here it can, and means so Fe3 will be oxidized. Sorry, Fe3 already oxidized. It will be reduced, and then it will form to Fe2, and then Fe2 again to oxidize to this one will form. So this reversible reaction will happen on the electrode surface. Now see, you can see here 1, 2, 3, 4 target here, and this space you can see the. I mean, I saw here only one, but there is lots of Fe3, Fe2, right? Lots of potassium ferrocyanide, ferricyanide. There is so many. So in this area only electron can flow, but other area electron cannot flow because they are blocked. So that's why you will get somewhat you will get some electron flow in this region, but in this region no flow. In this region will be little bit flow. But if there is no target, if you can remove all the target, then you will get the highest electron flow. So you will get then lowest impedance basically, right? But if you fully immobilize the surface, all the surface, if you the coated by protein, means your target concentration very high, then your whole surface will be covered by all the target. Means it will form a non-conducting protein layer. So it will hinder all the electron flow. So basically you will get highest impedance in this case. When your concentration will be highest, you will get the highest impedance. Yeah, tell me.
Sir, our purpose is to generate high impedance or just this the earlier one.
No, our purpose to measure our purpose to make a correlation between the impedance and protein concentration. This is our purpose. So our purpose is to make a correlation between concentration and impedance. So our purpose to make a calibration. In the y-axis, we will make the impedance, in the x-axis concentration. Now increase the concentration, get impedance. Maybe this is 1 nano, 10 nano maybe here, 100 nano maybe here, 1 micro maybe here, something like this. So now if you use some unknown concentration and measure the impedance, maybe this is here. So you can tell then from the impedance, you can tell what is your unknown sample concentration. So this is called impedance spectra. This is kind of, we can say, a level free electrochemical measurement. Why I'm saying level free? Well, until last biosensor, we need a secondary antibody that conjugated with gold. But you can see here, that is the level, right? This gold, this is level. But in this case, we are not using secondary antibody that conjugated with gold. So that's why this biosensor is called level free. We are minimizing the biosensor formation step. So in this step, so if your biosensor ready, you can just drop your target and you can wash the surface, you can measure the impedance, and that's all. And that impedance corresponds to how much target concentration you can say. Make it clear. Done. Okay.
Sir, from where the efficiencies come?
From where?
The efficiencies.
No, this is the this is the actually K3 epicene whole C, that's salt. So this is actually cation, this is the anion, right? This anion contain Ap3 ion. Now this Ap3 and this is actually K4 epicene whole 6, this salt. The cation will release, the cation will be here in the solution, cation K plus in the solution. So we are considering the reaction between iron Ap2 and Ap3. Okay. Clear?
Okay, sir. This we have to add in the electrolyte solution, no, sir?
Yeah. Means that's what I'm saying. Means, okay, I'm saying here. Means first, see, this is your sensor ready, right? This will be available when in the market. These sensors will be available for the user. So user, what he or she will do? He has to drop the sample. So if it is content target, then it will bind, right? Then you have to wash the surface. Then that is not bind, they will go out from the surface. Then user will be provided a tube that will contain some salt solution. That salt is the FeCnL whole 6 3 minus and 4 minus. I mean FeCnL whole 6 4 minus. This solution. You have to drop this solution in this sensor surface and measure the impedance. Clear?
Okay, sir.
Clear now?
Yes, sir.
Good.
In the below is not clear. This plot,
Which one not clear? Which one?
this plot below the diagram.
Oh, no, just now I'm going to just this part is done. Now I'm going to the second part. I not started this diagram. Diagram I will start now. Yeah, tell me. Who are asking questions?
So this is Bratin.
Bratin, yeah, tell me.
So do we need to use any blocking protein like BSA for the covering of any unoccupied space in this case?
Yeah, see, in this case, definitely to minimize the non-specific. See, in this case, non-specific binding is little. I mean, not that much a problem. Generally, non-specific binding is problem for the secondary antibody when you are using the gold. That's a very big problem in non-specific binding. Here, non-specific binding almost no, right? Because you are not using secondary antibody. But still, tell me.
But sir, there are many OH groups are there on the transducer surface, and the protein has sometimes protein has some kind of charge, so there might be a
right. But still, although here is non-specific binding very low, but this unoccupied surface you should block, because that you mentioned somehow maybe when you are adding the protein, right? Before adding the protein, you have to add some BSA. Why? Because that protein, instead of binding here, maybe they can bind here. Right, Bratin?
Yes, sir.
Instead of that protein binding here, they can bind here. This is basically non-specific. You will not get any correlation. Only you will get correlation that is binding with the antibody, not here. That's why, although here secondary antibody will not there, but still to avoid this binding, you can add BSA before adding. So that the sensor that will be available to user, basically it will be this transducer that will contain some linker and primary antibody. Then you have to add some washing buffer that contain BSA. So basically they will block the other unoccupied area. So that protein that you told, that will help to minimize the protein binding to this area. So basically they are very small molecule and electron can basically will flow through this easily. They will have some that is called this is called some I mean some nano size. I mean if the electron is very small size, small, right, they don't need any kind of very small gap is enough for them. So that's why if there is some small gap, I mean if not it's fully covered by protein, the electron can be easily pass through this gap. But if it's almost covered, then it will be I mean 100% block is not possible by the protein, because electron can go easily through the small gap. 100% gap block is not possible.
But
Okay.
sir, if the BSA is blocking the unoccupied space, then BSA is also increasing the impedance factor.
Yeah, you are right. That I am going to show you actually next next few slide. Yeah, here that I'm going to show you, but just wait few minutes. Actually, you are going more advanced. Okay, I'm going to show you here. Okay, that I'm going to show you. Okay, let's come to the first graph then. But still now I'm not showing you the graph, right? Just the fundamental thing I taught you, right? Let's come to the graph now. See, when so this is the sensor surface. So and this is the antibody, and we are adding here some Ap3 and Ap2 solution. So this Ap3, Ap2 actually, suppose your see, when you are adding any electrolyte on the in the solution, I mean when you are adding an electron on the electrode surface, they are forming actually somewhat a double layer. Do you know this double layer means? So like some cation you are adding, right? So if your electrode somehow negatively charged, so what will happen? So this positively charged, I mean the positively charged like ion will be here on the surface, and some then on this negatively charged ion also will be there. So some like this way they will form a double layer. So it is kind of the capacitor. So we are considering this one as a capacitor. So so in the capacitor case, this is kind of so we are thinking on the electrode surface when we are adding some electrolyte solution, because of some double layer formation on the close to the electrode surface, this is kind of capacitor. So on a capacitor we can say very simple circuit something like this. So it should have a RS. RS means the solution resistance. When electron will flow, so it will flow through the solution, right, guys? It will flow through the solution. So if you are using like, so if you are using like 10 millimolar concentration of salt, and you are using 100 millimolar concentration of salt, so 100 millimolar case the RS will be very low, and 10 millimolar case RS will be the high, right? If there is a high concentration, the solution resistance will be very low. Clear? So there is a relation. There should be a parameter of the solution resistance. So electron can flow easily. If the solution is the lower conductivity, then electron can flow slowly. So it's saying that the concentrations of the electrolyte is a factor for the electrochemical impedance. The solution of the solution conductivity is a good factor. CDL, this is called that I put. If you think about the capacitor, this is the capacitance of this double layer. Okay, and RCT. RCT means this is the actual parameter we will measure. This is, as I mentioned, that we will measure the impedance. Actually, we will measure RCT. What is the RCT? R is the resistance, C is the charge, T is the transfer. So RCT is the charge transfer resistance. This is charge transfer resistance. Okay. So this RCT value we will measure from the impedance graph. And ZW, this is actually this is called DI means this is a constant. There is some name, constant name. This is something like I also right now I can't remember. This is a constant. It has some name. So I can tell you the next class what is the ZW means. This is something like the constant we need to make this full circuit. So I'm not going to discuss the whole mathematical part. There is some mathematics. So I will give you a textbook. You can just read, but that is not important for the biosensor design. So just for the simple, just for understanding, just I am showing it is here that CDL, this is kind of a capacitance. RCT we are going to measure through our electrochemical cell, and this is a constant. They will be the series connection and CDL will be the parallel connection. So that description for that, if you want to learn the more details, maybe I can take you some few more extra class, but let's finish some biosensor design first. But if you want to learn the mathematical part, everything, maybe I can take one more class for that. Okay, I'm not going for the mathematics here. Is it okay for all of you guys? Okay. So if you want to learn then why it is the serially connected, why this is parallelly connected, for that we need some mathematics, some expressions and some derivation. Maybe that I can teach you some extra class. Just try to remember that we will measure the RCT from the impedance spectroscopy. Okay, guys, is it okay for all of you?
Yes, sir.
Yes, sir.
So okay, so we'll get, because just for this class I'm just skipping this derivation. So basically when you will measure the impedance, so you will get this kind of spectra. So there is two kind of shape. One is the semicircle shape, you can see semicircle, this region, and one is the straight line region. This semicircle region corresponds to actually your impedance. So if your surface, if you immobilize on your surface more and more protein, so basically this this will be increased. This will be increased, and you will get one straight line. This is because you have some electron transfer. That is called the mass transfer or electron transfer. So this straight line will be controlled by mass. Why I'm saying mass? Here. So like this one can be transferred on this surface. This is the mass transfer. I mean some ion can transfer through this hole or through this area because this is not covered by protein. This is mass transfer. Right? So electron transfer basically can occur from this region. This is mass transfer. So this is corresponds to this straight line. And this semicircle line, this is corresponds to this protein layer. So if there is lots of protein layer, you will get a big semicircle line. So if there is very small protein layer, then there is, mass can transfer easily, right? Then basically you will get the straight line instead of getting the semicircle line. Make it clear first. This is very, very important. Is it okay? Clear? I can repeat. Guys, can I repeat or is it okay?
So for mass transfer part, more electron will be released in the solution.
Right. So this is actually electron release. And this region, actually this is called why this is called the kinetic region? Because it is controlling your mass, kinetics. It is faster or slower. Faster or slower, right? So if it is too big, electron is the slow. If it is too small and you are getting the large straight line, so this is actually too small. Your electron transfer is very, very fast. So it is kinetically faster. And this straight line is actually your electron will, it's showing as it is you are getting high, very big straight line. means mass can transfer easily. So I will give you one example. I'll give you an example here. Suppose here, this one, right? So this is better example. No, this one. See, so this is only blank surface. So this is blank. I mean, almost you can say there is no antibody, nothing, only electrode, only your transducer. Actually, there we didn't draw here straight line. The straight line will be like this, like this. See, if the surface is blank, then mass can easily transfer, right? Electron can easily flow, right, guys? Is it okay? If there is no protein, but because of some thing, we still some other layer we use. That's why we will get some resistance. Some resistance we are getting, but very small, but we will get very long straight line. It lends. So here, so we are measuring, as I said, RCT we are measuring. So what is the RCT? That I will tell you. That I told you the definition. How we will measure that I will tell you again. So this is the RCT. So again, here RCT2, here RCT1, here RCT3. See, as this increasing, this one, this is bigger and this is the biggest, right? So basically RCT increasing. So if you're increasing the see here protein, so just one antibody you immobilize, the RCT increase. Then you add the target. So basically they are hindering the electron transfer. So RCT again increase. And this straight line you are getting, see, bigger straight line, smaller straight line, and smallest straight line. So in this case, you can say that actually kinetically the reaction becomes slower and slower, and mass also transfer rate also going slow and slow. That's why RCT increase and increase. So now I will tell you how we will measure the RCT from this graph. So see, one thing I told you, in the solution we will get some resistance. So solution itself, it has some resistance, right? So here, this value. That's why it will not start from the zero. It will start from something. This is the RS, solution resistance. And RCT value is the total semicircle region. Means if you put the full semicircle and the intersect of the this x-axis, this actually this x-axis, this is the impedance. Actually here we are measuring the real value. In the y-axis also we are measuring the impedance, but here is the imaginary value. As I said again, this is the mathematical term is there. Why the both axis is the impedance, right? Generally the we are measuring something respect to something, right? But in this case, like chrono amperometry, current versus time. But in this case, we are measuring impedance versus impedance. In the x-axis, we are measuring real impedance. In the y-axis, we are measuring some imaginary impedance. It is something like impedance is something like x plus iy, something like this equation. So there is some I imaginary part is there. But that mathematical part, maybe I will teach you one day. I will take one class. Otherwise, it is very difficult to understand. But I will going to give you those information that is useful for the biosensor design. Only those information I'm going to give you. Otherwise, other expression no need to keep in mind. That is fine. So only for biosensor design, I'm going to tell you the important information today. But if you're interested, I will take one class.
Sir.
Yeah, tell me.
Sir, previous slide. Yes. Sir, R ohm, what is R ohm resistance?
Yeah. So this one, na? So this is the R actually. Yes. Yeah, this is R is equals to the RS solution. You see, this is okay. I mean this much. Okay. So and this value is the RCT value. So RCT value means this is the total as I said you that this value is it corresponds to your RCT value, this semicircle region, this value.
Okay.
So this is the RCT value. And
sir, decrease in omega, what is sir omega? Decreasing omega.
Decreasing, this one. So decreasing omega, this is the see in the impedance basically we are applying some frequency. So we are applying higher frequency higher frequency to lower frequency. So we will start from, so when actually this is better actually for this class. If you, when you will come to the IIT Kharagpur, one day you can contact me. I will invite you to my lab. I will show you
Oh,
to all the
okay.
instrument. This is actually better thing. You should have one practical class basically, right?
Okay.
I think this is very good. If you have one practical, you should have one practical class. But as you are this pandemic time, you are in the home, so I cannot show you in the instrument because there is some parameter. There is some parameter design. Uh, there you have to plot. I mean, which range you are applying this impedance. This range you have to apply some frequency, some lower, higher frequency to lower frequency. One day I will invite you. So if you are in the IIT Kharagpur, if you are not the, I mean, total final year student, if you are not leave IIT Kharagpur, please contact me while you'll be here. I will show you all the technique in the instrument. Okay. I think this will be very good for all of you.
Yes.
Hmm.
Sir,
Huh.
sir, why we use importance imaginary part of impedance in this case?
Now, see, actually, because of the equation, as I said, this is a mathematical equation that I am not showing today. But I already uploaded our textbook, and I can upload one more textbook. There, actually, you can see all the derivation. There, actually, we are measuring the real part, not the imaginary part. So this part we are not measuring. We are measuring only this part, x-axis part.
Oh,
Okay, we are not measuring the imaginary part. So because of the equation, as I said, the imaginary part coming, but we will not measure the imaginary impedance. We will measure only real impedance one, that RCT.
okay, sir. Okay.
Okay, so this RCT
Okay.
we will measure. Now come to here.
Sir,
Tell me.
impedance, why it decrease? Protein is removed after some point.
Where, no. See, as I said, we are not taking the impedance for the imaginary part. We are taking the impedance of the real part. And this is actually something like this behavior we will see in the spectra. It is something like increase the imaginary, then decrease the imaginary. So basically, your real, that total, that impedance you are getting, that is this much. That is the RCT you are getting. That is not decreasing. You can see here. I will show you this example. So that impedance never decrease when you increase the target concentration. This is the real example. See, this is number 1 electrode, number 2 electrode, number 3 electrode. So number 2 electrode, what is the difference between 1 and 2? Tell me, what is the difference between number 1 and 2?
One in primary
Diameter
antibody.
increases, sir.
Yeah, not diameter. So here primary antibody immobilized. So basically protein immobilized, right, on the surface. So because of this, see, the diameter, total diameter, oh, you are saying the graph. Yeah, diameter, see, in this one, so here diameter increase, right? So it means if here, if you RCT1, RCT means this much, semicircle as I said, if you interpret, so this is the RCT, this is the RCT. So here you can say, so this is the RCT, see, increasing, see? So if you again add some protein, see the RCT increasing, right? So RCT1, RCT2, RCT3. So it is there higher. Okay. So I will give you some practical example one.
Sir,
Suppose
RCT is due to the resistance offered by the protein targets, right, sir?
yeah, that RCT offered by the not only target, by any kind of hindrance molecule. It can be the protein.
Okay.
So here in this case protein, right? See,
Okay, sir.
that last time Brotin said, see, suppose you have the electrode. So you are adding antibody on the surface. So after that, if you add some BSA to block the unoccupied surface, because of this protein, also electron transfer rate can be decreased. Then again, so impedance. So if you think about RCT1, this is the RCT2. If this is the RCT3, and if this is the RCT4, if you can see, so RCT1 will be the much lowest. This is the lowest one. Then RCT will be the, higher than RCT1 because some antibody is coated on the surface. Then again, you are adding some BSA to block the surface. Then again, it will be increased, right? This will be increased. Now again, you are adding some S mutant, some bacteria. Bacteria means some other foreign particle you are adding, right? So they will hinder again the electron transfer rate. They added. So this one again will be increase. Clear now? Brotin, now is it clear for you?
Yes, sir.
Okay. So is it clear, all of you guys? Is it okay? Why RCD increasing?
Yes, sir. Clear.
See here. So one thing here I mentioned, this one I am going to say SH. So what is SH? SH is called thiol group. Thiol SH. So this is functional group. Now, like COOH, this is called carboxylic group. Like NH2 amine group. So SH is the thiol group. So if your antibody contain thiol group SH, and if you drop on the gold surface, actually gold and thiol, they have very strong affinity. This is also called affinity. Affinity. So if your antibody already conjugated with thiol, and if you drop on the gold surface, so they will bind easily. So this is kind of the conjugation method on your surface. How we can conjugate your antibody on the surface. This is kind of another method. So you can make some thiol group on your antibody and you can drop on your gold surface. So your surface should be gold then, in this case, very specific gold. And like the avidin biotin, so gold and thiol, they have strong affinity and they will bind on the surface. And if you wash it, then you will get only antibody coated gold surface. Make it clear. Okay? Guys?
So I have a doubt, sir.
Tell me.
So like in previous one, in the sandwich biosensor, the first we have added our primary antibody, then we adding our target, then the secondary antibody conjugated with some gold nanoparticles, then some products will come by the reaction, then we'll apply some potential so that the electrons will be released, and these electrons will give some curve on cyclic voltammetry. But here we are not using any secondary antibodies or gold nanoparticles. So how the reactions are happening to release the electrons? So by the electrolytes.
By the electrolytes?
Yes. These electrolytes are causing the release of these electrons, sir.
Okay, Vibhuti. Yeah, nice question. So again, I will discuss. This is also a very good question. See, although I already told you, but I think you just missed it. Again, I will describe it. So as I said, last time for chronoamperometry, chronocoulometry, as I say, can you remember? Chronocoulometry case, this is the secondary antibody, this is gold, right? So we are adding some substrate, we are getting product. Okay, Vibhuti? Then this product will be oxidized and we will get this electron. Right. This is for chronoamperometry, chronocoulometry case.
Yes, sir. Yes, sir.
So in this case, what is the rate determining step? So how many electron you are getting? Right?
Yes, sir.
So if you are getting more product, so you'll get more current. This is the rate determining step, right?
Yes, sir.
But in this case, where rate determining step is you're the hindrance kind of thing. I mean here you are what you are measuring. So this your reaction is fixed. Last time you are increasing your electron transfer rate by making more. By producing more product. If there is more nanoparticle, you are producing more product, and that product can be oxidized. You will get more and more electron. But in this case, here number of the electron is fixed, like 10 electron is fixed. Now, if all 10 electron pass through this electrode, then you are getting lower resistance. Now, because of the protein covered the surface, now all 10 electron cannot pass through this here. Maybe 5 electron, then 2 electron, then 1 electron, right? Then like this way, number of electron actually decreasing because of the protein layer. So here number of the total electron is fixed, and that you are making a hindrance because of a protein layer formation. Make it clear. Okay, Vibhuti?
Yes, sir. The electrons will be same. Yes, sir.
But last time you are making some reactions, and more reaction, you're getting more and more electron, right? right? So
Yes, sir.
and that case actually you are getting many electrons. That's why you are getting higher current. Although by increasing the target concentration, there are also some protein layer forming, but because of the too many product forming, means because of the one product you are getting many electrons. That's why your net current actually increasing there. So if you can remember in the chronocoulometry also, see the target concentration is some protein layer also forming, right? Chronocoulometry case also.
Can you
But
take the attendance, sir?
Sorry?
Can you take the attendance? I have another class.
Oh, you have another class. Okay. Sure. I almost done. So I will finish this class today. So just keep in mind, so we have exam on Monday. Okay.
Yes,
Okay.
sir.
So on
We have
Wednesday,
class.
right?
So Wednesday we have one discussion, questions answer we'll discuss. So I will upload this slide also. So please tell me if you have any questions, we'll discuss. Then Monday we'll take exam. Okay.
Okay.
Okay, sir.
So this is the impedance, right? Like this way we can measure the impedance. So basically like this way. So
8th will be the exam.
sorry, 8th Monday.
Okay.
Monday is the 8th, right? 8th of February.
I thought you said 10th.
No, I thought it's the 10th, but because we have the Wednesday discussion, let's finish it on Monday. Okay. I will send you an email.
Okay, sir.
Okay. So I think I will stop the class today. I think that's all for today also, because how we are measuring the impedance, this thing, why it is increasing. So now, if you have any question, you can ask me. Otherwise, maybe we can stop today. Maybe Wednesday we will discuss again. I will give you some question sheet, maybe 10 or 15 questions I will bring, and we'll discuss together on Wednesday. Is it good for all of you if we can bring some questions and we can discuss together? Okay.
Yes, sir.
Yes, sir.
So before the
Okay,
exam,
sir. Okay, sir.
we can discuss, right?
Okay,
Yes, sir.
Okay, good. So Wednesday, then maybe 10 to 15 questions I will bring. Then if you want to repeat any point, then I can repeat again, so that you can clarify.
So syllabus will be till today, right? Including Wednesday's doubt session.
Including Wednesday doubt session, then that is the syllabus for first exam.
Okay, sir. Thank you, sir.
Until impedance.
Okay, sir.
Okay. I think already 8:30, right? We should stop this class today. That's fine. Okay. That's all for today then. So if you have any question, you can ask. Otherwise, you can leave then. Thank you, all of you.
Have
Thank
you
you, sir.
taken the attendance?
Thank you, sir.
Thank
Yeah,
you,
I
sir.
took
Thank
the
you, sir.
attendance.
Okay, sir. Thank you.
See, guys, if you have any suggestion, you can discuss. So we want to make this class more informative and more attractive for all of you. I think it is good for all of you, right? This class.
Yes, sir.
Yes.
I'm learning something.
You will learn
Yes,
so
sir.
many topics. So in this class, you will learn not only one topic, many topics will come. This is basically a very interdisciplinary subject, right?
Sir.
Hello.
Yes, sir.
Hello.
Interdisciplinary.
Hello.
Hello.
Tell me. Brotin,
Sir,
tell me.
sir, in this particular method, you used gold thiol group interaction. So, does the bioconjugation method affect the final RCT value?
Bioconjugation means which one? I mean, this thiol or maybe some amine group, these
Yes.
things.
Yes.
See, when you are developing a biosensor, these things should be constant, right? Always. Yeah, it can affect. Maybe when you are applying some amine group, so that you have to. I mean, when you are optimizing your biosensor, that you are checking. So maybe you can check one by thiol, two by avidin, three by amine formation. Then you can get which one is the best. You can optimize. This is kind of some optimization step you can make before finalizing your biosensor formation. That you can do. That is
Sir,
one kind of research you can do.
yes. Sir, our initial goal is to decrease the solution resistance, right?
Yeah, definitely, because initial goal is the very bare goal, right? So it is very conductive. The electron can transfer through this electrode very easily. You will get a very low RCT. I mean, your structure will be almost straight line. There is no actually this one semicircle, almost straight line you will get.
So, then if we use the EDC NHS bioconjugation system, then the number of layer will be increased, right?
That's
Then
thing.
the thiol group SH thing.
Right. This is actually a very good question. Actually, when you will be in my lab, that time I will discuss with you again. Generally, we are avoiding many steps. That's why when we are forming the biosensor, I mean, the antibody finally it will be here, right? So maybe step by step, like 1, 2, 3, so many steps you can do. That's why we should use. That's why I told you. Sometimes we are using the graphene oxide or reduced graphene oxide, so that at least we should have very good conductivity, right? This surface. Otherwise, if you just maybe gold, then you use the like EDC NHS, carboxylic acid formation, then EDC NHS, then antibody. There is so many steps. So they actually heavily hinder the electron transfer rate. So basically, your signal will be decreased, right? Signal basically will be decreased. So that's why you should use some very conductive nanomaterial like reduced graphene oxide, some carbon nanotube, or some very good nanomaterial you can use. So on the nanomaterial, maybe you can immobilize like EDC NHS process. So basically, although you are forming so many steps, but this nanomaterial will compensate that one.
Okay, sir. Okay, sir.
That's
Understood.
good. That's very good question. So slowly you will understand. So basically you should read many papers. When you read many papers, then you will understand these things. So why they are using nanomaterial basically on the surface. Basically, this is the main reason.
Okay, sir. Thank you, sir.
I think that's all fine today for all, right? Okay.
Sir, the impedance part will come or not, sir?
Now impedance part, yeah, because Wednesday we are going to discuss again, right?
Yes, sir.
That's the impedance part will include. Huh? Okay. I will upload this slide by tomorrow. I will upload. Okay. Good night, all of you.
Good night, sir.
Good night, sir.
Good night, sir.
Good night.
Thank you, sir.
Thanks, guys.
Hello, sir.